Okay, so today we'll talk about the atomic model. Why do we have this model that we have it now? And what is the evolution slash revolution that the atomic model have had from the moment that the scientists was wondering what are the fundamental particles of life. So the biggest question that every scientist has, especially physics and chemistry, is what are the fundamental particles of life? What are those particles that are present on every matter of life? And this started with Aristotle. Aristotle was wondering what are those fundamental particles of life. And he said that there are 4 elements: fire, air, water, and earth. And those are the 4 elements that are part of the every matter in life. Those are as well numbered as a principle, so dry, hot, moist, and cold. However, we know now that there is more into it. And Dalton was the one that brought the 5 postulates of chemistry. Okay, so he is kind of the father of the chemistry, and the 5 postulates that he has are kind of summarized on those slides here. So what we are especially interested now, is that matter is composed from invisible atoms, and the word atoms actually means indivisible, so you cannot divide it any further. And the idea of Dalton was that every matter is composed by tiny spheres that are not divisible, and they are attached with each other, they are close to each other. Each element in Earth consists of characteristics that are unique to that element. They are unchargeable, meaning that more than unchargeable means that they are with a neutral charge. And when different elements are combined between each other, they form a different structure, which is known as the molecule. And there are defined numbers of atoms on each element. You know this from chemistry. And in chemical reactions, atoms are neither created nor destroyed, but they are rearranged, which is the conservation law of charges. What we will be focused for the physics part is this one here. This is the very important one, because we have matter is composed by indivisible atoms, which means that you cannot divide it further, and that is the fundamental particle of life. However, later on, Dmitry Mendeleev, which is a Russian scientist, was actually a mathematician, but then there was not enough classes for him, so that he was placed in chemistry department, and then therefore he did what he knows how to do best. He organized all the elements in the nature into a table, which initially was known as the Mendeleev's table, periodic table, and now is simply periodic table. It's known simply as the periodic table. You have seen that periodic table. It is even in your data booklet. However, through that sorting, there were some mistakes that were done in sorting them. So not all the rules were followed. So let's say some of the elements with the smaller mass or the heavier mass were before the elements with a less mass, which was the base principle of organizing the elements in the periodic table. But he was so convinced that those elements belong on that specific place, the vertical column, because they had the same chemical characteristics. Then later on, this periodic table that initially was organized by Mendeleev was done some work from Henry Moseley, which organized them or told us that the way that the periodic table is organized this way, even with the jumps that Mendeleev's table had, is based on that is known as the atomic number. And then later on, we come to J.J. Thomson model of the atom. So we were established on this Dalton, and chemistry was fine with every Dalton's principles. Okay, and chemistry was fine with everything that they were working on. Every experiment was satisfied with that, so as long as the theory is there, then the theory, and it satisfies the results of the experiment, the theory has no reason to be challenged. However, after that, we move to the J.J. Thomson model of the atom. J.J. Thomson model of the atom is something like this, that atoms are tiny spheres, mostly positively charged, surrounded by plasma that is mostly positively charged, but you have negative charges that are embedded into that plasma. Okay, this model of the J.J. Thomson model of the atom came as a result of that is known as the cathode ray tube. So if an experiment is done and the explanation is not on the satisfying the explanation of the results of the experiments are not explained based on the theory, then what is happening, the theory changes. And then it is, in this case, what happened, J.J. Thomson had made an experiment which is known as cathode ray tube, and the results of the experiment were not satisfied with Dalton's model of the atom. Then what he discovered, then within the atom we have two charges, positive and negative, okay, that are balanced. So the number of positives is the same as the number of negative. And this made him to present a new model of the atom. So let's explain a bit what is cathode ray tube. This experiment involves a vacuum tube. This is the vacuum tube. That has a high voltage induction coils. The anode is it's known as the anode, this one here, and the cathode. Okay, The phosphor coating was painted at the end of the tube so that the phosphor coating was painted here, so that the strike of the electrons were stuck into that phosphor coating, and it is the strike of the phosphor coating, and then it is shine. It makes it shine. So as the ions were going through the cathode and anode here in this in the first area here, then the motion of the charges or the motion of the particles was straight across. And then what was noticed there was that here there was a spot that it was shined, okay, because this being a phosphoric coating, phosphorus coating will make it so that it will glow. Then what J.J. Thomson did, he installed a set of parallel plates. So a set of parallel plates that were attached to the cathode ray tube. And then as he was changing the set of the parallel plates, the voltage of it, then he noticed that the glow, the glow on the phosphorus coat was going up or down depending on the polarity of the parallel plates. Okay, and then what he did, he installed a solenoid in which he was producing a magnetic field through the tube. And then he noticed that the charge was going in the different direction, so was deflected. Okay, I will bring another picture here so that we can. So in addition, when J.J. Thomson applied both the electric and magnetic field, like you see it here on the picture, then what happened was that the path of the stream was straight again. So what he did, he was able to figure out that the fact that it is going undeflected, that means that you have two forces that are equal to each other. And since you have parallel plates, then you have electric force. And since you have a solenoid producing magnetic field, then you have a magnetic force. So now, being between two parallel plates, so the electric field force is Q times E. And being in a magnetic field, then magnetic force is QVB. After simplifying this, we find that V is equal to E over B. And this is the start of the electromagnetic part of modern physics. Once J.J. Thomson has determined the speed, then what he did, he turned off the electric field, okay, and then measured the radius in which the particles were deflected. But now we know that if there is no magnetic field, then the path, since the magnetic force is equal to centripetal force, the path will be uniform circular motion. So then QVB is equal to mv squared over r. And then from here, you can find the radius, or not the radius, because we didn't know that time that there was single particles, but the charge to mass ratio as being a V over BR. Okay, so even J.J. Thomson didn't know if the electrons were able to move or the ions were able to move. But what he figured out was that that is known as the charge to mass ratio. We'll bring some examples here and then we'll discuss that. So the example is a student performed a cathode ray tube experiment. The magnetic field strength from the coil was 0.040 Tesla. The parallel plates were set apart 3.0 millimeters. And in order to produce a straight cathode ray beam, 3600 volt was applied across the plates. When the electric field is turned off, the cathode ray tube are bent into a radius of this. What is the charge to mass ratio of the cathode, this particular particle? Okay, so first we will calculate the speed. So in order to calculate the speed, we will use the fact that electric force is equal to magnetic force, or QE is equal to QVB. So since we are dealing with the same charge, then V will be equals to E over B. Or in our case, will be the E, which is delta V over delta D, because we are between the two parallel plates, and B, the magnetic field strength that we are dealing with. So in this case, will be 3600 volts over it is 3 millimeters, which converted into meters will be 3.0 times 10 to the power of negative 3. And this is over 0.0400 Tesla. And then from here, we find that the velocity as the particles are, or of this particular ion is 3.0 times 10 to the power of 7 meters per second. Now we move to the second step where we calculate what is the charge to mass ratio. So that is based on the fact that the centripetal force is equal to magnetic force, or mv squared over r, the v that we just found, is equal to qvb. So this is canceled out, and then from here, the charge to mass ratio will be vb over r. vbr, or 3.0 times 10 to the power of 7 over b, that is still 0.0400, and a radius is given now as 4.26 millimeters, or 4.26 times 10 to the power of negative 3 meters. When you enter this into the calculator, you will figure out that the charge to mass ratio is 1.76 times 10 to the power of 11 coulombs per kilograms. Through this experiment, J.J. Thomson tried different metals for the cathode, but he always found that the same charge to mass ratio, which was 1.76 times 10 to the power of 11 coulombs per kilogram for all cathode ray particles. Therefore, the same negative particle was always coming from the cathode. Okay. Let's bring some another example here. So in a modified Thomson experiment, when the hydrogen atom beam is exposed to a magnetic field of 0.400 Tesla in an electric field, again, the same numbers kind of, they are 3 millimeters apart. When the electric field was turned off, the particle was observed to move with a radius of this. So let's see now what is happening with the charge to mass ratio of the hydrogen ion. So again, the first step is we will find the velocities using the fact that electric force is equal to magnetic force, or Q times E, which is the electric force of a charge being between two parallel plates, and QVB, that is the magnetic force of a charge moving into a magnetic field. So then V will be equal to E over B. Is the same as the example that we did before. So delta V, because we have parallel plates, over V, and then we have 3600 volts over 3.0 times 10 to the power of negative 3 to convert it into meters, or 0.0400 Tesla. Then you will have a speed of 3.0 times 10 to the power of 7 meters per second. And then after that, you find the charge to mass ratio. So using the fact that magnetic force is equal to centripetal force, or QVB is equal to mv squared over r, then one of the velocities is cancelled out, then charge to mass ratio will be V over B times R, or 3.0 is the speed that we just found using the fact that it is going undeflected, over 0.0400 times now the radius being 0.7 meters, 7.8 meters. So it is 7.8 to 8 meters, and then we will find that the charge to mass ratio of the hydrogen is 9.58 times 10 to the power of 7 coulombs per kilograms. Okay. Further on through the a lot of experiments, was discovered that cathode ray tube particles were neutralizing the hydrogen ion into one-to-one base. In other words, the electrons and the proton have the same quantity of charge, but one was negative and the other one was positive. From the difference in their charge to mass ratio, G.G. Thomson concluded that a proton has a mass of 1700 times more massive than the electron. And then later on was accepted that the correct ratio would be 1836. So the mass of the electron is less than the mass of the proton. So through this experiment, J.J. Thomson discovered that particles were smaller than what Dalton has imagined. So he discovered the electron. And yes, the electron, he said that the electrons are bended into that material, that plasma that atoms have. But what it did is, this is the discovery of the electron, or negative and positive charges within the structure of the atom. And this work led us into that is known as the subatomic particles of physics. The subatomic particles, it's accepted to be the building blocks of all atoms. So proton, electron, and later on, James Chadwick discovered that and confirmed the presence of the neutrons as the third building block of the electron. Now, you have the video for the Millikan soil drop experiment. And the Millikan soil drop experiment was at about at the earliest of 1900. And what the main finding of the Millikan soil drop experiment was that charges are quantized. So they are multiples of the elementary charge. Okay, Millikan finding experiment is that charges are quantized. So are multiple of a charge, but later on, or through the work that J.J. Thomson did, discovered that this is the charge of the electron. Okay, what was happening in the Millikan soil drop experiment, and I strongly recommend you to watch that video. What was happening in the Millikan soil drop experiment, an oil charged, which was negatively charged, was in place between two parallel plates, so that the oil drop was suspended, was in equilibrium. So if we have a picture of the oil experiment, what you will see is that the equilibrium is happening between the force of gravity and the electric force that the oil drop is experiencing. So then if we have like in the case of the general statement, then what we will have is force of gravity is equal to the electric force. And the force of gravity, we know that is mass times acceleration due to gravity, and electric force for a charge being between two parallel plates is E times Q. So then from here, we can find what is the charge as mg over E. Or for that matter, we can find the mass or the electric field strength between the two charges as well. However, let's bring a question here and let's see what is the charge of the oil drop in that situation. So now we have an oil drop with a mass of 8.0 times 10 to the power of negative 15 kilogram, and between two parallel plates that are 5.0 millimeters, or 5.0 times 10 to the power of negative 3 meters, and with a difference of potential energy of 1.225 kilovolts, or 1.225 times 10 to the power of 3 volts. And what is the charge that the oil drop has? So again, we will start with the fact that the electric force is equal to force of gravity since it is suspended. This is the key here. Or QE is equal to mg, and from here Q will be mg over E. Or if we substitute what we have here, so will be 8.0 times 10 to the power of negative 15 times 9.81 over electric field is delta V over delta D. So will be 8.0 times 10 to the negative 15 times 9.81 over delta V is 1.225 times 10 to the 3 over 5.0 times 10 to the negative 3. So then you will have that the charge is 3.2 times 10 to the power of negative 19 coulombs. Now, based on the fact that the charges are quantized, so from this is the main finding, this charges are quantized is the main finding of the Millikan soil drop experiment. And through work that J.J. Thomson had, we discovered that the charge of electron is 1.60 times 10 to the power of negative 19 coulombs. And this is known as the elementary charge. Combining Millikan's work and J.J. Thomson work, we can finally figure out what is the mass of the electron and the mass of the proton. This is how we do it. So let's deal with the electron first. What we know is that the charge of the electron, charge to mass ratio of the electron is 1.67 times 10 to the power of 11 coulombs per kilogram. And if we are dealing with proton, then charge of the proton over the mass of the proton will be 9.58 times 10 to the power of 7 coulombs per kilograms. Now, therefore, we do know that the charge of the electron and the charge of the proton is equal to the elementary charge. So this will be E over the mass of the electron is equal to 1.76 times 10 to the power of 11 coulombs per kilogram. And mass of the proton will be, or elementary charge over the mass of the proton will be equals to 9.58 times 10 to the power of 7 coulombs per kilogram. So from here we find that the mass of the electron is 9.11 times 10 to the power of negative 31 kilogram, and mass of proton is 1.67 times 10 to the power of negative 27 kilograms. Okay, this is for the lesson, and I hope that you understand. We'll go over it in class as well.